Okay, we are live. Good morning, good afternoon, or good evening, depending on the place of the earth where you are now. We are starting now the third day of our professional training on GNSS, signal processing and navigation techniques. Welcome everyone that are already connected to us now, and I would like to welcome Felix, Adria, and Andre too. Um, you can send your comments and your questions by chat. We are already receiving your comments here in the chat. The materials are already available to download in the event website. I will put the link in the chat in a couple of minutes. And today we have the presentation, the break, and the second part of the presentation. And after the break, we will have an explanation about the possibility of scholarships. Stay with us to attend this part of the presentation, and you can know more about this possibility of scholarships. So, Andre, Felix, good morning, good afternoon, and welcome.
Good morning.
Good morning. Welcome, everyone.
Good morning.
Okay, I will start sharing my screen, and I will continue with the course. Oh. Okay. Yeah.
Okay, Felix, everything okay with your screen sharing and also your audio? If you have any problem, I will tell you. I will open my microphone and I will tell you.
Yes, please. I hope I will not hit the button today on my headphones that is muting.
No problem. No
muting the microphone. Try my best.
Okay.
So yeah, good morning, everybody. Thank you, everyone. Good morning, everybody. Welcome to the third day of this professional training. Yesterday we talked more about the signals of GNSS and more about the characteristics of signals, properties of signals. Why are they designed like this? How do different systems, what's their design? We touched a little bit also the topic, how did the design of GNSS is evolving, and what is also going on in the modernization of the systems. Today, we are going to enter the signal processing part. We touched already a little bit the signal processing part at the end of the first lecture yesterday, where we were introducing the time delay estimation very roughly. And I already commented, okay, we need to initialize somehow this iterative process that we have been discussing about, which ended up in a formulation that is a basic delay lock loop for the time delay estimation. And we can see today the topic is signal acquisition, and this is exactly this initialization process, and we will see this again. Today we will also introduce the Doppler to this problem, because the delay and Doppler, they have to be initialized in such a way, otherwise correlation cannot be achieved. If the Doppler estimate is not good enough, we cannot achieve high correlation, and therefore enter the tracking stage, so the time delay estimation with the iterative process that we have, or feedback process or feedback system that we have roughly or shortly introduced. After the break today, we will continue and deepen then the discussion on this feedback system. So today, let's start with the signal acquisition. and we will focus on one specific method to do the acquisition, but I will mention the names, or at least the categories of the other methods. So yeah, we have a short introduction on receiver processing as an overview. Then we do Doppler and time delay estimation. We will discuss the detection problem, so detecting the signal and estimating the parameters, initializing the parameters and detecting the signal. And then we will have a look into the parallel time delay acquisition, which is one of the possible ways of performing acquisition. Yeah, so this is it's an overview of the general receiver signal processing. Very basic. So in principle we have two states. One is acquisition, one is tracking. Acquisition is the rough estimate of the parameters, and this will initialize the synchronization of initialization of synchronization parameters, and this will initialize the tracking. And then if the tracking is lost by some reason, maybe the SNR gets bad, or we have maybe too fast, the parameters are changing too fast, then we talk about that we have a loss of log. We need to detect this loss of log, but it's not so difficult to do this. And then we need to kind of restart this process. So we need to reacquire and start the tracking. With the acquisition, we also need to we need to do two things. We need to initialize the parameters, and we need to detect which satellite is present, which one can we receive, because we are on some place on the Earth. There are like 30 satellites on their orbits around the Earth, and we don't know where we are, right? We want to calculate the position. So we don't know which satellites can we receive. So we have to try all the codes in the direct sequence CDMA approach. So for GPS, Galileo, and Beidou, we have to try all the codes, and we have to check which satellite is available. So we need to check how, and this is simply done by checking the receive power. So we're varying the parameters in time delay and Doppler, and we're looking for a peak that should appear for some Doppler and delay value. There should be a peak appearing if the satellite is present, if the satellite is received. If the satellite cannot be received, we don't have any peak, so we just receive noise all the time. So and this is the problem of acquisition. So we have a detection problem combined with a parameter estimation problem. The tracking we will discuss more in detail later today, but this is following this feedback system that we already saw, for which led to a delay log loop. We then have for each of the parameters we can build a feedback system for the phase, for the signal phase, for the Doppler, and we can combine these feedback systems to work together and keep track of the parameters. Here on the right-hand side, we also see again the interface with the second part of the course. So with today, with tomorrow and Friday, where these estimates are passed from the tracking to the what's called navigation processing, PVT, position, velocity, time processing. There's a lot of names for this, but this is in principle, it starts with all the observables from the satellite, so the parameter estimates, and then we enter this field of positioning. You maybe wonder why is there so many stages? There's also approaches where we talk about direct positioning, which means that we take the parameter estimates of the complete estimator are already X, Y, Z of the user, and we use the observables from the input is the signal already. There is also an approach that's called direct positioning, where we are not splitting up everything in these steps. But the current implementations that you you can buy today. Receivers pretty much follow this logic here. This is a very simple logic. You can build like a state machine also with all the different aspects. I mean, you need to detect from the tracking. You need to detect: am I still in lock or not? Can I try? Is this still an estimate, or is this just am I following noise here all the time? So you need to figure out: have you locked on the satellite signal? Have you lost lock? So there are some methods how to detect this, and then you, in order to build this these processes here, or to follow these errors, you have to take some decisions, right? So you have to, first of all, you have to also decide: have I acquired a satellite? And this is what we will discuss with the detection problem. But are the parameter estimates sufficient? You cannot really test this. So most of the receivers, they initialize tracking and then they check if they have locked. So they have like it's called a lock detector. So they are checking if they are following or some parameter estimates with the feedback system that makes sense or not. And then if they decide, okay, this is not we're not tracking a satellite here, so then they go back to acquisition and acquire again. In the acquisition, you can also follow many strategies, because you have to search. You don't have to search through all the satellites. Yeah. So there is because this takes time. You have to search, not have to search through all the satellites. Maybe you have some side information from internet or other systems that tell you, hey, you are roughly in this area, so you should only look through these 15 satellites instead of all 30, you know. So this helps to have a faster acquisition. Acquisition is maybe one of the most demanding or most complex, so from computation, complex, the most complex part, because we have to do a high number of it's in the grid search and the search to satellite. You have to do this very fast, because you want to navigate, right? So if if your receiver is already running and turning, then it's navigating all the time. But if you switch it on, then it takes a while, because it's not only the acquisition time, but also you have to receive the navigation data from some source. Sometimes this is fast, sometimes this is not so fast. In acquisition, there's these terms, cold start. So cold start means if you acquire from no information, then there's a warm start where you have already information. And I think there's there's also these categories, but it takes a while until you can start navigating. So maybe you have experienced it also already when you use a navigation system in your car, and you start in a garage where you have no reception of the satellites, and the problem is that you want to exit the garage, and then you want to start navigating, sometimes in an environment that you're maybe in a city that you don't know, and then the first turns already are crucial, right? So, but it will take some time. It will take some time until you're ready to navigate. So, and this time you have been maybe wondering, what is the receiver doing? He is acquiring the signals, and he's doing these initial estimates, and he's then waiting to receive the navigation data in order to get you the first position fix. And then there's some numbers. We will not go into the details of these measures. For acquisition, there's the time to first fix, so the TTFF. Sometimes you can find this also on the manufacturers will tell you about this, and they will say, okay, cold start TTFF, warm start TTFF of the device, and this will tell you, okay, how fast can I start navigating. Okay, so this is the the overview of the processing. We will deal in this part now with the first part, so with for the one on the left. Far left, acquisition. yeah, what does acquisition do? We already talked about this, but let's go through this again. Provides a rough estimate of the signal Doppler shift and a time delay. It solves a maximum likelihood estimation problem in a coarse resolution. And this coarse resolution has to be chosen that fine in order to start to initialize the tracking well. There's this connection between acquisition and tracking. So the parameter estimates from the acquisition, they need to go smoothly into the tracking, and the tracking should lock in fastly with these estimates. So the estimates need to be reasonably accurate already. And we have discussed this already yesterday. We found out, okay, we have to hit with the autocorrelation function of the signal, we have to hit the peak, the global optimum. We have to be close to the global optimum. We need to hit in our case, the concave region around the global optimum. If we don't, we can end up on a side peak then and track the side peak. It's not bad. We can still follow the signal, but we will have a large bias in the range. Yeah, it detects also the received satellites, as I said, because the satellites are separated by the code. So we need to understand also which satellite can we receive in this moment, or in this instant we want to acquire. For each satellite, correlator outputs with the same time delay and Doppler shift from different epochs and periods are used to form a decision variable. If the decision variable passes a threshold, the signal from a certain satellite is assumed to be present, received. Time delay and Doppler shift estimates are used to initialize the tracking loops. So let's have a look. How can we estimate a Doppler and time delay? We go back to our signal, and now we are introducing the Doppler and the phase to this signal. Remember, before we had a signal without the phase and without Doppler, and then our signal also was real. Now the signal is getting complex in baseband, and so we have a complex model here now with also complex Gaussian noise. So we have here on the left-hand side, we have again our vector for the period k. That's the vector signal x. We have it at time instances with a sampling duration of ts. Then we have the noise now is also complex at time instances k capital NTS up to k capital N plus capital N minus 1 t times ts. And then we have the vector of the sampled and delayed sequence or code. This is the signal of one satellite. So we are assuming that we receive one satellite plus noise. Then we have also the Doppler shift. So this is the frequency shift here at the time instances, yeah, because the Doppler is this is a model that this is a shift, right? The Doppler, or in fact, the Doppler is a dilatation effect in the signal, so it stretches the time axis and the frequency axis in a certain way, or in a certain way. So this is what the it's a dilatation effect in the spectrum. However, if the bandwidth is not so large, we can assume that this can be modeled by a shift. So this, you have to be aware of that this is a model. The original Doppler effect, the frequency shift is dependent on the value of the frequency. If you go back to the theory of Doppler shifts for electromagnetic waves. So for higher frequencies, the shift is higher, so it's a dilatation effect, like a harmonica when you pull it, but this can be modeled by a simple shift, and this is done in many applications, because then it can be treated in the receiver just by a multiplication with an exponential function. So here the Doppler frequency is nu, and then we have this Doppler frequency in hertz, nu in hertz, and the sampled version of it. Then we have here this so we have C, and then there's a circle with a dot. You see that in the equation. That's the Hadamard-Schur product. This is the element-wise multiplication. So we're multiplying the first element of the vector C with the first element of the vector D. And then the second element with the second element of the other vector, and so on. The result of this product is a vector again with the multiplications of the respective entries of the two vectors. And we also, as you can also see, we have this phase now. So the carrier phase phi we have in here in our model, and we assume that this carrier phase phi is constant over this period k. It can be changing with k, so we could also introduce a dependency on k, but it can also change or slower than the periods. So yeah, we have here the Hadamard-Schur product. Yeah. Okay, so that's the new model, the refined signal model. G of k, remember that this is the symbols, the navigation data symbols that are modulated onto the spreading sequence and the signal. So we assume that the signal is filtered with an ideal low-pass filter following our simplified baseband model that we introduced in the first part of this course. And thus the noise is complex, wide Gaussian noise after this sampling incident or sampling stage, even if we choose an ideal low-pass filter. So HL is an ideal low-pass filter with a bandwidth of B, and then we choose the sampling rate exactly to be 2B, and then we can show that the noise is still so the noise samples that are coming out of or after the noise samples after sampling, they're still white. So this means that the expectation of this vector here is 0 over k. The expectation of the norm of the vector is n times sigma n square, while sigma n square is the standard deviation of the noise, and the product so of this matrix, we build a matrix here, n times n Hermitian. I explained n, so Hermitian is a complex complex conjugate transpose operation. So we have here a column vector multiplied with the complex conjugate of the row vector, respective row vector. And this gives us an identity matrix. So this I of n is an identity matrix where we have only ones in the diagonal and zeros in the rest of the matrix. And it's a scaled identity, so it's multiplied with sigma n squared. Yeah, we assume that the quantization noise and terminal noise from the antenna and the LNA are included in this noise variance. So we can have here the variance of the quantization noise. Be careful with quantization. I mean, if you have more than 4, 5, 6 bits, this noise can be assumed to be a complex Gaussian. So it's an addition to the white Gaussian noise simply. This is what we assume here. If you go down to 1 bit, 2 bit, and so on, the noise cannot be assumed a white complex Gaussian anymore. Then you have to apply other models for the modeling of the noise and also of the signal. We will assume here that we have more than like 6 bits or 6, 8 bits for the signal available. And then the quantization noise can be assumed as white Gaussian noise with a standard deviation of sigma q square. Here. Yeah, for maximum likelihood estimation, we again take just one period, so the first period of the signal, and call that vector x, and then we assume that this vector x is a realization of a random variable x, has multivariate Gaussian probability density function PDF, parameterized by the parameters, and we now define here the parameter vector. It's parameterized by tau, nu, so time delay, nu the Doppler frequency, phi the phase, p the power of the signal, and g of 0, which is the received data bit of the signal. So we have all these parameters. We see now here that our model in the term of the exponential function in the denominator we see that the signal model is now following all these parameters, and we do that, and they're following it for the first period. We now again choose to use the likelihood here. So this is the the probability density function of the random variable x, parameterized by theta. Again, the likelihood is a function of the parameter vector theta, which is to be estimated at a given realization of the random variable x, while the PDF is a function of the realization of the random variable x for a fixed value of theta. They have the same form, but it depends on what is fixed, okay? In the case of the likelihood, the realization is received, and we're trying to find the parameter vector theta that matches best this realization. And this is what we're trying to do. Set up our maximum likelihood estimator. We will try to now reparameterize this problem a little bit. So we will pack the phase, the power, and the symbol into the variable alpha, and we will define a parameter vector tau nu alpha now. So now that we can, again, as already before discussed in the course, we can build another maximum likelihood estimator here. So this time for a vector parameter. We had defined this for a scalar parameter, and now this is a parameter vector. We are maximizing the likelihood with respect to the parameter theta, and we are also we can, instead of maximizing the likelihood, we can also maximize the log likelihood. Let me check. Okay, okay. The connection is back. So the webinar tool told me that my connection is not good, but I think we're fine, right?
Yeah, everything is okay, Felix.
Okay. Good. Yeah, my computer told me to change the resolution of the screen, so I did that. So let's continue. I'm sorry for this. I hope we can continue without any interruptions now. So yeah, instead of maximizing the likelihood, we can also maximize the log or natural logarithm likelihood. And as discussed before, then our formulation gets much easier, because if we apply now the logarithm to the formulation of the likelihood or the probability density function, the PDF, we end up with this formulation here in the likelihood. We can plug that into our optimization problem, and we see immediately again that the first two terms, so log 1 minus n log pi phi 6 sigma n squared, this is not dependent on the parameters that we define, so we can drop these parameters for the maximization. So we only have to consider the third term, and expanding now the third term. So the norm remember the norm of a vector x is x Hermitian x. So we can also calculate this L2 norm here. So this 2 bars with the squared with the 2 subindex. This is equivalent to everything that's inside. This is a vector times the Hermitian of the vector times the vector itself. So we can now expand this norm. We can also drop the 1 over sigma n square because it's not dependent on the parameters that we are interested in. And we have then these terms, these 1, 2, 3, 4 terms. Again, the first term, the x Hermitian x, is not dependent on the parameters. We can further drop this also. And we can then write our final cost function with these remaining 3 terms. So this is the function that we want to maximize with respect to the parameters nu, tau, and alpha. What we can do first is we can take the derivative of this function with respect to alpha. This is at the global optimum of this function. The derivative with respect to alpha should be 0, right? So we can build this equation and say, okay, at the optimum point where we have the optimum estimate for all the parameters, the derivative of this function should be, so the gradient of this function should be 0 because we should be at a global optimum. So we can also do this with respect to alpha conjugate. You can also try to take the derivative with respect to alpha. You end up with the same formulation. This is just more convenient. We end up there with only 2 steps now. So we have, if we take the derivative of the 3 terms with respect to alpha conjugate, so the first term we have alpha conjugate. The second term we don't have any alpha conjugate, so it's 0, the derivative of this. And then the third term we have alpha conjugate again. So, and we equate that to 0, and then we arrive at an estimate of alpha based on the optimum values of tau and nu, right? So, and we can write here the denominator. We can just put n here because the normalization of the sequence is so the c Hermitian times c is n, and d Hermitian times d is 1. And we can just stay with this here. So with 1 over n. So we have c of t Hadamard d of 0 nu Hermitian times x. That's the estimate for alpha. We can now plug this estimate back into the cost function and substituting with this alpha hat in the cost function. And we arrive at this final cost function for the time delay and Doppler estimate. We cannot further simplify this. But again, you can see this is cross-correlation, right? So we have cross-correlation of the received signal now with Hermitian. We have, as the signal is now complex, the signal model is complex, we have to take this into account. So this has to be the Hermitian with respect to the model of the signal that we're using for the correlation. So that this is the reference sequence that we use, plus a Doppler probe. And we have to go through all the time delay and Dopplers that are possible to find the Doppler and delay estimates. In general, such a problem can be solved by a 2-dimensional grid search, gradient method, e.g., for example, Newton's method with good initialization. However, the problem needs to be convex, or in our case concave, then over the whole area of the parameters, and this is not given in our case, so we have to stay with a 2-dimensional grid search. We cannot apply a gradient search from the beginning, but as we have discussed already, the complete parameter estimation process in our approach is a two-step approach. First, grid search for the initialization, and then we use a gradient method to further refine the estimates. And the grid search is performed in a more coarse resolution with respect to the parameters. The signal phase here, so phi plus minus pi, considering a g of 0 being minus 101, and power p can also be determined using the estimate of alpha hat based on the estimates of the estimate alpha hat. So this alpha hat is the estimate of alpha based on the estimates tau hat, so the estimate of the delay, and nu hat, the estimate of the Doppler. So the argument of alpha hat then is the estimate of phi plus minus pi, which is coming from the symbols. And the power is the absolute valued square of alpha hat. This is an estimate for the signal power in our case, because we have normalized our model such that the signal power then is the absolute valued square of alpha hat. So we can derive immediately all the parameters of interest if we have found the estimate for tau and nu, tau hat and nu hat. So how can we do this? So we will decide, or we have to perform here a grid search. So the final cost function that needs to be evaluated is also called cross ambiguity function. You can also find this with radar systems, signal processing for radar systems. They have the same problem. Radar is trying to estimate Doppler time delay of a received signal as well. They have the same problem, and they also use this term cross ambiguity function. And for the kth period, so we can CAF. So CAF is at the kth period with respect to tau and nu is then our cost function. This is exactly the cross ambiguity function. So this is the maximum likelihood estimator of the parameters. To select a suitable strategy to evaluate the CAF and thus to find its maximum, we have to inspect the shape of the CAF for the problem at hand. So we have to look at the shape of CAF for all possible time delay and Doppler values. Basic strategies in GNSS acquisition to evaluate the CAF are serial search. So we go through all these pairs of time delay and Doppler tuples of these values. They're also called bins when we talk about acquisition here, or in this related to acquisition, but they can be tuples or pairs. In the literature you will find delay bins and Doppler bins as the exact values of the grid search that we apply. Yeah, there can be parallel time delay acquisition. All possible time delays are evaluated in parallel for each Doppler frequency bin. This is the approach that we will discuss later. And there's also the parallel Doppler acquisition. All possible Doppler frequencies are evaluated in parallel for each time delay bin. So we will focus on the second method here. Yeah, how can we now formulate the detection problem? Signal acquisition determines the presence or absence of a satellite. And two hypotheses can be defined as the hypothesis 1 that says the satellite is present, and the hypothesis 0, then the signal is just noise. Okay, so either we have the satellites present, then we have alpha c of t Hadamard d of k of nu plus noise, or we have the signal is just noise for this respective satellite. If we only consider one satellite, and as I said, the satellites we can separate them by code, so this model also holds if we have more satellites present. Yeah, H0, also called the null hypothesis, is fulfilled when the desired satellite signal is not received. H1, also called alternative hypothesis, is fulfilled when the desired satellite signal is received. This type of detection problem is called binary hypothesis testing. We're clear because we only have two hypotheses. And for this we can formulate what's called likelihood ratio test, and following the Newman-Pearson lemma. To maximize the detection probability P of D for a given probability of false alarm PFA equals to rho, decide the hypothesis H1 if the likelihood ratio with respect to X, and then we can calculate the likelihood for the signal under the hypothesis H1 divided by the likelihood under the hypothesis 0. The probability of detection, I think this term is clear to everyone. Probability of false alarm is the probability that we falsely detect a satellite, or that we detect a satellite and there is no one. So yeah, there's even if we detect a satellite and there is none, or it's that the satellite is present and we do not detect it. So this is the probability of false alarm. In our case, it's there's also the probability of misdetection. Yes, so the probability of false alarm is only the case here as defined that we have this means we are integrating over all x with the property that the likelihood ratio is above the threshold, which means that we have and the hypothesis 1 is 0 is true, which means that we are detecting a satellite and there is only noise. So this is the probability of false alarm. And then there's also the probability of detection. We can calculate this integrating the likelihood over all x with the property that the likelihood ratio is above this value gamma. So this is the threshold that we will choose, and then we integrate over the likelihood with respect to the hypothesis 1. So what we have to give for the design is the probability of false alarm. So this is the given value. We can evaluate now for a given rho. We can find the value gamma based on this integral, and then we can calculate also the probability of detection based on the likelihood ratio. Yeah, is called the likelihood ratio. And I just put this here to be complete. We have discussed this. So the Lx of theta of H1 and Lx of H0 denote the likelihood for hypothesis H1 and H0 respectively. Yeah, so since the likelihood with respect to H1 is the likelihood that there is a signal plus noise, we also have the likelihood if there's only noise. This looks like this. So we have no signal present, only noise. The likelihood ratio can be given, so we can calculate this ratio again based on for this It's very simple to calculate, right? So we have the term 1 over pi sigma n squared to the power of n disappears. We have two exponential functions, one in the denominator, one in the denominator, and then we get here to this formulation, and this needs to be above the threshold. If this is above the threshold, we achieve a certain probability of detection and probability of false alarm with our detector. So what we have to do is we have to evaluate the likelihood ratio, have a look if this is above the threshold, and if it's above the threshold, we have achieved a detection with a certain probability of false alarm and a probability of detection. Yeah, we can take again the logarithm on both sides, and we can then write. So this makes it much easier to formulate it. So we have then on the left hand side we have the exponential function is we just take the argument of the exponential function. On the right hand side we have the logarithm of the threshold. Rearranging again, so we can on the left hand side we are rearranging the norms. We end up with this formulation larger than the threshold, and we can immediately reformulate this again, because this we can further reformulate this, because as you remember, the third term here in the first equation is alpha conjugate, starting with alpha multiplied with alpha conjugate. Remember, the absolute valued square of alpha is the power, so this is equivalent to p. And I pointed out earlier that the CT Hadamard D0 nu Hermitian CT Hadamard D0 of nu, this is equal to n. So we have p times n, and we can pack this on the other side, and this is then not dependent anymore on the parameters. For any value of tau and nu, this is given that this term is n. Here the multiplication of c of tau Hadamard d for the 0th period of nu Hadamard Hermitian with the same vector is equal to n. So then we have on the left hand side only these two terms left, and we have modified the threshold on the right hand side, and we can we can say that because on the left hand side this is the same complex number, but so the first one is the conjugate of this, so it's the same complex number added, so it's the complex number added with its conjugate, and we can write this as twice the real part of this complex number, and we see this in the third row here on the third equation, then that we have the real part of alpha x Hermitian c of tau Hadamard d at the period 0 of nu is larger than sigma n squared log of the threshold plus pn divided by 2. And this is then our new threshold, then can be given by gamma prime, and we have to define gamma prime based on the noise variance, the power of the signal, the number of samples that we took, and we have to divide that by 2. In case so this would be the case that if we know the parameters, we can perform this test. Yeah. In case now the parameters are not known, we have to, and this is our case. Yeah. So if the parameters in theta they are not known, we can define the detector to decide on the hypothesis 1 if. And this is now called the generalized likelihood ratio test. And this is here now the generalized likelihood ratio. we take an estimate of the parameters, right? So we can estimate and then compare the based on the estimate with respect to the threshold. And this solves the problems that we talked about. This now solves the problem of getting the initial estimates for our synchronization parameters, and on the other hand, detect whether the satellite is present or not. Okay, so where theta hat is the maximum likelihood estimate, or theta hat maximizes the likelihood x parameterized by theta for the hypothesis 1. An equivalent form is to decide now for this hypothesis 1 if we maximize this ratio, the generalized likelihood ratio. And this means that we maximize the likelihood ratio for the parameter estimate that maximizes this. So we are jointly performing now an estimation and detection problem. Maximizing, we can also maximize the log likelihood ratio we get, maximizing the logarithm minus the logarithm of the hypothesis. So the likelihood of the hypothesis 1 minus the logarithm of the likelihood of the hypothesis 0. And then we can also again reformulate this with the same rules that we had before in the Doppler and time delay estimation. So first we can take the derivative of this above cost function with respect to alpha, plug alpha back into the cost function, and we end up clearly with the maximum likelihood estimator on the left-hand side. For the time delay and Doppler, and we have on the right-hand side modified the original threshold gamma. We have to multiply it by n sigma n square. Based on this, we have, based on this, we have now, this is the solution for our time delay Doppler estimation and detection, satellite detection problem. And we can reformulate that this is the CAF, right? So this is the cross-ambiguity function. So we have to find the maximum of the cross-ambiguity function with respect to tau and nu, and then compare the value at this maximum value of the CAF with the threshold. And the design of the threshold is based on the Newman-Pearson lemma or theorem that we had discussed earlier. We can define a probability of false alarm that we tolerate, and based on this we can calculate the probability of detection and the threshold, so gamma. So this is a design step. So we design our acquisition false alarm, and from this we can calculate the threshold, the probability of detection, and then we have to evaluate here now in the grid search the CAF, find the maximum of the CAF, and then compare it to this modified threshold. So how can we do this in practice? So the parallel time delay estimation or acquisition. First, we define the discrete Fourier transform again. So just to repeat this, so the analysis equation for the discrete so the discrete Fourier transform, sorry, it's not the discrete time Fourier transform, it's the discrete Fourier transform. So the DFT of the signal x of n can be given here is x of m, and we can also use the operator DFT. So DFT of x of n is the discrete Fourier transform. The synthesis equation, so to achieve the inverse DFT, is just given here below, and we can use the operator DFT inverse for that. In case of a finite sequence x of n, a shift in time or in frequency only makes sense as a circular shift. So we can define now the circular shift properties. here. So the DFT of x of n minus n0 modulo n is equivalent to the exponential function minus to the power of minus j2 pi m n0 divided by n times the DFT values of x. And the other way around. So we have then the shift in frequency domain can be given here in the second relation is the DFT of e to the power of j2 pi m0 n divided by n times x of n, and this is equivalent. So the DFT of this is equivalent to x m minus m0 modulo n. The modulo operator can be defined as if a modulo b is a minus b, and then this operator with these brackets that are incomplete is a rounding operator. So this is a divided by b, where this operator x of these incomplete brackets is equivalent to the maximum of q, where q is element of z, so the integer numbers, but including the negative numbers, integer numbers, and this is q is each smaller or equal to x. So for example, if we have minus 4 modulo 5, so this is minus 4 minus 5 minus 5 divided by 5, and we take the highest integer value of this. So this is minus 4 minus 5 times minus 1. So in the end, this is 1. Or also 4 modulo 2, so 4 minus 2, 4 divided by 2 is equivalent to 4 minus 2 times 2, and this is 0. So this is the circular shift. Consider two finite duration sequences. So we are now discussing the circular cross correlation, and we will use that for our parallel time delay estimation acquisition. This is what the last slides are about. So if we have now two sequences x1 and x2 of duration n, we can build the DFT of them. And the endpoint circular cross correlation, can be calculated by the sum. So we're now calculating a cross correlation between the two, and it's circular. And this is then the sum over p from 0 to capital N minus 1 x1 conjugate times of p times x2 p plus n modulo capital N, and n is from 0 to capital N, and the result is z here. We can also write this in the endpoint DFT of z of n can be given as z of m, and then the double sum over n and p times x1 conjugate p x2 p plus n modulo n multiplied with e to the power of minus j2 pi mn divided by capital N. So this is the definition of circular cross correlation. How can we reformulate this cross correlation? So we can further reformulate. So as you can see here, we can, on the right hand side, we can split that up. The exponential function originally here was minus j2 pi mn divided by n, and we can rewrite this as two exponential functions, one with the to the power of minus j2 pi m p plus n divided by n, and one exponential function e to the j2 pi m p divided by n. Now we can reorganize the terms because the last term is not dependent on n. So the last exponential function and the function x or the sequence x1 conjugate of p. So we can write this now as a multiplication of the two sums here. One is only dependent on pm and capital N, and the other one is dependent on small n, p, capital N. And we can further reformulate this. The second part here is the shift, right? Is the DFT, is the shift of the DFT of x of 2. And now we can also see that the first sum is the DFT of x1 conjugate, and we arrive at the multiplication of the DFT of the two functions. So the circular correlation of two sequences is is equivalent to the DFT of the first sequence conjugate times the DFT of the second function. And we can use this in our acquisition process now. So in practical problems, it is convenient and quite efficient to derive the circular cross correlation as the DFT of x conjugate multiplied with the DFT of x2, and then taking the inverse DT, the DFT, and we arrive at the time representation of the circular cross correlation. What is the circular cross correlation? This is exactly the search that we have to perform, but for all delays, right? So we get, if we do this now, x1 and x2, multiplying the DFTs, one is the conjugate of this, and taking the inverse DFT, we get all the values for one Doppler bin. We get all the time delay values. However, in the resolution of the sampling sequence of the sampling duration of the sequence, that's the resolution that we can estimate the time delay. But as we discussed before, we only need a coarse, a very coarse resolution here. And this is sufficient to start the tracking in most cases, in all cases, if we only have the resolution of the sampling. Because usually we have at least 2-3 samples per chip, so we are already in a sub-chip resolution, and this, as you had seen, is needed for also signals with higher order Borg and so on. Yeah. So matrix representation of the DFT matrix in an n by n symmetric matrix Wn, where the mnth element is given by, so the mnth element of this matrix is the exponential function to the power of minus j 2 pi mn divided by n. We can then reformulate the DFT and also the IDFT, so the inverse DFT, by using this elements of the matrix, and we can build if the DFT of a vector x can be given as, so we multiply the vector with this matrix. So I'm trying to develop a formulation now for our vector signal. So let's say that this is and x of f is the vector of the DFT of the elements of the vector x. So the IDFT then can be given as multiplying x of f with the inverse of the matrix Wn from the left-hand side, and we arrive at the vector x again. The following interesting properties are fulfilled by W. So W inverse is equivalent to 1 over n times W conjugate. The Wn times W conjugate is the identity, and W conjugate is equivalent to W Hermitian. The DFT matrix Wn is a Vandermonde matrix on top of that. So you have a lot of nice properties, but they're not so important for our course here. But the matrix has nice properties, the DFT matrix. Yeah, how can we apply this now? We can now exploit the formulation of the circular correlation using the DFT to perform a parallel time delay search for each Doppler bin. So we have for each Doppler frequency nu, we can perform here the Hadamard-Schur product of the vector Xi and Xi conjugate. This is equivalent to the CAF for a specific Doppler value, as you can see, over the different sampling instances. So the time delay is equivalent to the different sampling instances. And this is the vector F in our case now, where the vector Xi here, you can see this is the implementation of the circular cross correlation with applying the DFT matrix. So we have the received signal, we have to build a model signal C of 0 in our case here, Hadamard-Schur with dk of different Dopplers. So we have to use if you want to translate, you can directly translate this line in a code in a program. So you have the inverse DFT represented here by this inverse DFT matrix. Then we have the DFT of the incoming signal at time instant k or period k. We take the conjugate of that. And then Hadamard-Schur with the DFT matrix multiplied, and we take here the model of the signal is 0. So C, the time delay is 0. Because we are calculating the circular cross correlation with respect to this model. Then Hadamard-Schur with the Doppler, the sample Doppler frequency for a certain Doppler value. So we have to probe different Doppler values from here where the Doppler bins and the evaluated time delays are. So the evaluated time delays, as I said, so T in our case is an element of the domain D. This has to be D tau. I have to correct this. And this is equivalent from 0 to capital NTS. And nu is equivalent of D nu. And this is equivalent to nu min, which is a minimum value and a maximum value up to nu max. And we have a resolution of the Doppler bins of delta nu. So we have to evaluate the vector F for all these values nu from this domain d nu. While in general you can understand that the relative velocity between user and satellite, we have rough estimates for that. If the user is not moving, then a Doppler search between -6 and 6 kilohertz, between -6 kilohertz and +6 kilohertz is sufficient. If you are moving also, then you have to take this into account. But anyway, we end up with a limited search space here for the Dopplers, and then you only need to decide on the resolution of the Doppler for your acquisition. But you see, this is a demanding process because we have to evaluate now the vector F for all of these Doppler bins, and we have to perform to do 2 DFTs and 1 IDFT. It's not this can be quite complex depending on the implementation, but in the end we can form a CAF matrix then for all these probed Dopplers, and we can create a decision. We can then probe all the entries of this matrix as for our threshold from the detection problem, because one column of the matrix, these are all the time delay values, right? So the columns in our case are here the Doppler bins, and in the we have in the the column. Yeah, one column is one Doppler bin, and we have in the row in the rows, we have the time delay estimates with respect to the resolution of the sampling frequency. So Fij is an element of the matrix F, and we have then to probe all the elements of this matrix F for our threshold. For each, and we have to do this for each PR sequence, we have to define one of these matrices. So you see, we have to calculate for each satellite, we have to calculate or evaluate or calculate a matrix F, and we have to probe each value to the threshold. In case a satellite was detected using the GLRT, the maximum element of F is used to derive the initial estimate. So the element that is above the maximum above the threshold is maximum and above the threshold. We use this for this element of the matrix defines us then by the column the Doppler frequency, and by the row the delay estimate. So we have solved our detection problem and estimation problem with the generalized likelihood ratio test, implemented a parallel time delay search using the DFT to calculating the circular cross correlation, and the resolution for the Doppler has to be chosen such that the following parameter tracking process can be initialized properly. This is also what we discussed. So in this case, we can only choose the Doppler resolution, and we have to make it that fine that that the tracking can start with this parameter. So it's sufficiently close to the true value. Again, this has to be chosen by the designer. As you are designing your feedback system, you have to go back to your acquisition and say, okay, I have to acquire this exact in order to start this feedback system and to keep track. How does this CAF look like? Here's an example, and here we can see directly that the CAF is not in its whole for all the possible Doppler values and time delays. It is not concave. There's a concave region, and we see this, and we even see this is I derived this from data from my laboratory. So I have recorded a GPS or a GNSS signal, and I have performed this acquisition with this is from real data. And we can see the triangular shape because I'm using a GPS CA code signal with a rectangular chip pulse shape, and I have used a 6 megahertz bandwidth, I think. So it's very close to being having this triangular shape. However, here I think this is only the peak because we have only like 2 values. We have 3 values per chip, around 3 values per chip. So these are the 3 values you can see here. But it is like a triangular shape. If you have a higher sampling rate, you can see the triangle. Here we can see mainly the global peak, and where the global peak are, if we look at the respective row and column, we can get the Doppler and delay estimate. So yeah, this is it for the first session today. We could start looking into some questions from your side. So please, if you haven't done it so far, please write them fastly in the comments, so we could discuss now about the of some questions, about some questions. 9:45. Okay.
Okay, thank you, Felix, for your presentation. So we have time for a break now, a 15-minute break. And then after the break, we can talk about the questions, the comments, and also about the opportunities for masters and PhD
Yeah.
in GNS.
Okay.
Okay, so let's do a quick break.
Okay. See you in 15 minutes.
And, okay, at 10, let's do a 20-minute break. We will return at 10:05.
Okay.
5 past 10, okay?
See you then. Bye.
See you there, bye. Hello, we are back from the break. Before we continue, I think we could talk about the opportunities for masters and PhD. So, André, Adria, or Felix, when you want, you can start.
Okay, maybe I can start with some information about opportunities at UFC in partnership with ITA. So yeah, so I am André de Almeida. As you know, I am a professor at the Federal University of Ceará, and also I am a professor of the postgraduate program in teleinformatics engineering. Well, I have received some emails from interest candidates applying for a master or PhD studies in GNSS area. So the goal of this short conversation is, I will first give you some very brief information about these opportunities, and of course, if you have questions, don't hesitate to leave the questions in the chat, or if you like, also send us an email afterwards. But let me briefly explain. So we have in the postgraduate program of teleinformatics engineering, there are different research lines, and I would highlight two of them, which are related to signal processing for communications applications. And another one is mostly focused on communication systems itself. And the GNSS research fits in one of these two lines. Of course, they are in the hybrid of these two lines. And our master and PhD programs, we have this is a 4-year period. Of course, as usual, we are in the same system as the American system. So 4 years for the PhD, 2 years for the masters. And we have calls for new students every semester. So every 6 months, some professors propose different subjects, and then the candidates apply for that. They must prepare a research plan, and this can be done, of course, with the help of one of the professors involved. So in the case of GNSS research, Professor Felix and me at the UFC and ITA sides, we are connected in the same research project, so we can offer topics that are related to GNSS research. So topics such as signal acquisition, time delay estimation, those topics that are you have seen very well in this in Felix talks. And once the students are selected, so once they are approved in this selection process, we can apply for scholarships. So this is what we have mentioned before. The scholarships, they are usually conditioned on the performance of the students in the selection process. So we look to the CV of the student, we see the experience, previous experience, either professional experience or academic experience, and there is a ranking of the selected candidates. And then we don't have, of course, scholarships for all the selected students, but there is a bunch of scholarships that we allocate to the students respecting the rank of those candidates in the selection process. These scholarships, they are funded by the Brazilian government. So they are funded by CAPES or by CNPq or by our state funding agency in Ceará, which is FUNCAP. And they are scholarships from these three funding agencies. And usually we have been able to let's say, to give scholarships to all the selected candidates. But this varies. There are some promotions where we have too many, it's very competitive in some senses, in other times it's not very competitive. So the allocation of scholarship is not guaranteed. but we have been able to accommodate that well to the students. What I could say more about that? Okay, there is an important thing that we have at UFC, and then I can pass the word to Felix to give you more information. There is a GNSS recording station of GNSS signals that are on the rooftop of our department. And these recording station, there is a small lab that has a receiver measuring GNSS signals. And this was a partnership that we have with DLR, the German Aerospace Agency. And this partnership let's say, was conducted by Felix since he came as a visiting professor to our university some years ago. Now he is in ITA. Unfortunately for us, but fortunately for him. But Felix can provide you some more information about that. I believe that this is a nice thing because the students can get involved with this recording station, can maybe use the recorded signals and apply that in their research, which give a nice value to the work. Okay, and I would just highlight that in the context of Galileo, of this GIC project, we also welcome students that are interested in joint supervision. And there we have at the Spanish side, Adria. Professor Adria is working on similar topics which are complementary to ours. And we also have opportunities to send those students to Spain for some internship. And there are some mechanisms for that. There are PhD, sandwich PhDs that can be applied, that can be funded. And of course, the students are welcome to do research visits in Spain, in the Polytechnic University of Catalonia, and also in ITA, where Felix is located. So, there is a very rich opportunity for internships, for cooperation, and I believe that that would be a nice thing of this GIC initiative. Okay. If you have any questions, I am there, of course, during the week, and don't hesitate to ask. I will maybe give the word to Felix and to Adria that can add more information on that. Thank you.
Yeah, maybe I can say a little bit more about the infrastructure at UFC. So we have two professional GNSS receivers. We have a recording system that can record 2 frequency bands. All the infrastructure is owned by the German Aerospace Center and also operated by the German Aerospace Center. But we have, from the side of UFC, we have an agreement that for research we collaborate with the German Aerospace Center, and we can use the data also working with our students. So if you are a student in the postgraduate program for teleinformatics engineering, then you can use these data. We are mainly interested with this station in research on ionosphere scintillations and also on tropospheric measurements. So, for example, extracting the water vapor in the atmosphere. We are looking into methods of robust tracking during scintillations, also looking into multi-frequency, multi-constellation impact of scintillations on the receiver. So there's a lot of things that can be done. We are working, as I showed today, we're working on all this different stages of the receiver, let's say, signal processing. So we're working in acquisition tracking, but we're also working in the navigation navigation processes, solutions, positioning solution optimization. So as you maybe have experience already with this, so working with atmospheric research, a lot of people work, they take the receiver as a black box and they work with receiver data. Adrien already mentioned the Rhinex data, for example, and you have a look at this data, which is the estimated the output of the tracking principally, with some corrections, and then you evaluate these data and try to learn some about the atmospheric and ionospheric behavior. This is, so we have on the one hand side learning about it, on the other hand side developing algorithms to enhance the monitoring and developing algorithms to be robust against this, because this in Brazil is a big issue. There's a lot of applications. They suffer from these scintillations every day, and especially the availability and the continuity that we discussed is severely affected by these effects every day, and we have to look for methods to enhance this, and this can only be done by enhancing the tracking of the receivers and the parameter estimation. So that's from my side. I'm very happy collaborating with my former and colleagues from UFC. I had a very nice time being a visiting professor there. We are still collaborating very closely in many aspects. Together with students and so on, and I'm very happy that we now have a third partner in this group with the UPC and the team of Adrian Jaume, who are working in the precise point positioning area, and this is a part that we are a little bit missing so far, so we can collaborate and join forces here to have a very nice future collaboration. I hope that you're getting interested in applying for these master and PhD possibilities, because then you can also benefit from all this. So thank you very much.
Okay, just to add a few words on what André and Felix mentioned, I have put a message into the chat with the website, with the part of the GIC website that was shown by Carlos Mirapeix, the coordinator of the project on the first day. Basically, if you go on this website, you have the description of the two research groups, the group at Barcelona in Spain and the group at Brazil, and then you can get an idea of what could be the possible research topics. And you will notice that both universities are very, very complementary, a little bit like the training that you are seeing here. There is a part on the signals and there is a part on the navigation. So how does it work, a double PhD or a double master? Basically, for the student, has to fulfill the requirements at both universities. The number of years, the number of credits at one university and at the other university, and they need to be harmonized. And this is done with an agreement between the two universities. But the agreement can only be signed, can only be started once that we have the candidate. So for the candidates that want to apply, they first need to be enrolled at UFC and then be into the program and be accepted at the program, and later need to be enrolled and accepted by the program at UPC. And then this double diploma agreement is signed by both universities, and at the end of the PhD, the student gets the double PhD, the PhD from the Brazilian university and from the Spanish university. That we think that it is a very attractive option for you. So this is from the academic point of view. The other part is the financial, and then financially we need to ask for a grant, and then we have different agencies, different funding agencies that can provide the financial support. But this is on a later step. First, we need to find the candidate. They need to fulfill the requirements, the academic requirements, and then we can apply for grants and so on. But the good news is that you have the opportunity, you have the will of 2 different universities to collaborate on having a supervisor from Brazil and a supervisor from Spain, and then having the double PhD. So we think that is a very good opportunity for you. This is everything that I wanted to say. I don't know if you want to add something else, Felix or Andre.
No, that's perfect. Yes, I think we have crossed all the important points. So, I mean, don't hesitate if you have questions. I have received, as I said, some messages from students, and we found interest to have this quick moment here after this break to give you some more information. But anyway, don't hesitate to write to us if you want to know more about these opportunities.
We cannot hear you, Eduardo.
I'm sorry. Okay, thank you, Andre, Adria, and Felix. Please just put your emails in the chat if it's possible, so people can contact you. The link with the information about the master and PhD opportunities is already in the chat. But thank you very much.
Yeah.
And now we can continue with the training. Felix, just one question for you, and maybe for the others. How much would it cost, or what would be the price ticket in a course like the one that is being held this week? And are there any similar courses available today for people to enroll?
Yeah. In the US, there's an organization called NAVTech. They offer professional trainings. They offer also that experts come to your company and they give training. I don't know about the price. I think I participated once to a course, but it was not the whole week, and this is then like $800-900, but it can be more if it's for the whole week. I think there's like colleagues of Chris Haggerty, John Betts, people that are very known in the area. They give these weekly courses, and I think they're more than $1,000. I mean, we try our best here also to give a very good quality course, and it's open or indirectly funded by the European Commission. That's it. We have this is funded by the GIC project, so it's paid by the European Commission. Our course here, and it's free for everybody. But yeah, there are these courses. I don't want to compare the quality of the courses. They're really good. I mean, John Betts, Chris Haggerty, they're very good presenters. They have a lot of experience. They have been involved in GPS for many years, decades, and they are very good in giving these courses. They have more lecturers. I have to check the web page. Maybe I can find the web page. I know of this. I know there is also the ESA summer school every year in Europe. Adrian can maybe say a few words about this. I think you're involved in this for each year, or?
Yes, there is the ESA summer school every summer. I think it's around July, and then it's about this price, 1,500 euros. Because it's funded by ESA, then there are some limitations on the nationalities that can apply to this ESA course. But depends on the course. I also know the courses that are given by the ION, the Institute of Navigation, just before the ION GNSS conference in September. I think it's 1 or 2 days before the conference that they have this short course on GNSS. So, and the prices are in those range per person.
Okay, thanks, Felix and Adria, for your answer. My point is, and I would like to tell everyone that is connected to us in this course, that as you can see, this initiative of the Galileo Information Center in Brazil is something unique in the Brazilian geospatial sector, course with this high level and quality. So make the most of it, take advantage of this course and these opportunities. Felix, when you want, you can continue with your presentation.
Yeah, I just opened the webpage. I have the price here. So the GPS fundamentals course for Navtech. Okay, that's a 2-day course. This is already $1,500, so $1,499. This is what they have as a price. I put the link here, and this is Chris Haggerty who gives the course. So yeah, it's take advantage of our course. Yeah, but okay, our course is funded by the European taxpayer at the moment. So because they have an interest in boosting the knowledge of Galileo, but yeah, I think it's try our best to have a good course. I can mention that, okay, my slides, this is the course I give at ITA. So we have a course on GNSS signal processing, and the slides that I'm showing, they're part of this course that I'm giving in the postgraduate program for electronics engineering and computer science at ITA. So, okay, and then let's continue with the parameter estimation. Usually I have two lectures for the parameter estimation, but I cut the material a little bit so that we have this as a brief introduction. I mean, if you are interested receiving more of the material, you can write me. I can send it also to you. Because that material is developed by the help of the Brazilian taxpayer, because I'm paid by the Brazilian taxpayer to act as a professor at the university, and my duty is also to develop these lectures and give the lectures. So yeah, let's talk about parameter tracking. So we have seen how can we initialize today in the morning, how can we initialize the parameter estimation, how can we detect which satellite is present, this is done by signal acquisition, and we have seen the parallel delay acquisition using the circular cross correlation, and then by calculating this with a DFT, so a discrete Fourier transform. This is nice if you want to implement this with any kind of the languages that are available. So Python, MATLAB, C. There are nice libraries for the implementation of the fast Fourier transform, and you can use that. So in a few lines, you can build up a code that is calculating already the CAF, so the cross ambiguity function for each Doppler bin. You can then build this matrix. So it's really only a few lines to do this, but be aware in a hardware implementation, implementing the Fourier transform and so on in a parallel hardware, this is includes a lot of complexity. We have then also a multiplication of the length of the signal, so the number of samples by the number of samples. We have to perform a complex multiplication, and we have to for the sequence 1 and the sequence 2, and the DFT of the sequence 1 and the DFT of the sequence 2. We have also to perform the inverse DFT. So don't. It looks like not much effort, because in code, this is in most of the more powerful languages, this is only a few lines of code. But yeah, in a receiver, this is the biggest part or have most complexity. After the positioning, the tracking, the closing, the tracking loops, as we will see now, is not so complicated, because we are relying on a feedback system, so a gradient method, and then this effort is very low. But we pay the price in the beginning. The initialization has the high complexity, and then the tracking has a much lower complexity. The positioning has again more significant complexity. However, the tracking is performed in parallel for all the satellites. But if you are interested, there's a lot of free software also available for signal acquisition and tracking. So it's easy to develop a small computer program, even working with real data, with this parallel time delay acquisition. And it is also quite fast, because you calculate all the time delays with one shot for each Doppler bit. So let's have a look at the outline of the parameter tracking. So I will give a short introduction today here on in the beginning. Now, what is the purpose of tracking? Then we'll have a look at delay and joint phase estimation. So we derived the maximum likelihood estimator already for time delay, joint time delay and Doppler estimation. Here we will derive the maximum likelihood estimator for time delay and phase first. So we will assume that the Doppler from the acquisition is exact enough to start with, and then we see if based on this, we can estimate time delay and phase. We have a look into the delay lock loop and the phase lock loop. And then later we come back to the frequency estimation again with the frequency lock loop. So for each of these parameters, we then have a feedback system. We could combine all the three feedback systems. There's also combinations where we only have a delay lock loop and a phase lock loop, because in principle, the phase lock loop can also estimate the frequency, because the frequency is the change of the phase over time. So, but we will set up an architecture here in this short introduction with all the three loops. But if you start reading about these tracking implementations, there's a lot of variants of this. There's always a delay lock loop, but some receivers, they switch between a frequency lock loop and a phase lock loop. So for the coarse frequency estimation, they use an FLL. No, the screen is not frozen. I'm still talking about at this first slide. Don't worry, everything should be fine. So there are some receivers that use an FLL for coarse frequency synchronization, or further refining the acquisition result, and then switching to a PLL. But there's also receivers that use an FLL and PLL in parallel, or assisted. So to assist the FLL, the PLL by an FLL, or vice versa. So let's start getting into this. So first, we want to understand what are the objectives. What are the objectives of parameter tracking? First of all, we want to refine the estimates of Doppler, carrier phase, and time delay that we got from the acquisition. I mean, we have been searching for Doppler and time delay in the acquisition, but we can, as we have seen with the parameter alpha, we can also immediately derive an estimate of the phase with an ambiguity of pi. Because of the symbols, we can also derive a phase estimate to initialize. Eduardo, is there some problem?
I think your screen is frozen in the first slide.
Oh, okay. Now I'm on the
The
second one. Okay.
I think you need to stop screen sharing and
Yeah, I'll
just
try to do it
share.
again.
Okay.
Thank you very much. So,
Now, yes, now we are in the second slide.
second slide.
Okay, thank
Okay.
you.
So let's see. Thank you very much. So this is the second slide. So you did not miss much. We can go back. So this was the first one. Here was the. So this was the first slide, and now we're on the second slide. So we want to refine the estimates of Doppler carrier phase and time delay. As I said, we could also derive from the parameter alpha from the acquisition. We can also provide, we can derive a phase estimate. Besides Doppler and time delay, we want to track Doppler carrier phase and time delay for each satellite over time. This is like the basic objectives. And now let's have a look into time delay and phase estimation jointly. So we assume now for the time being that the Doppler frequency shift was corrected based on the Doppler estimate provided by the acquisition. So we have multiplied the signal with e to the j2 pi nu of t, nu t, or minus, depends on how you implement this, but it's then minus e to the minus j2 pi mu nu t, and we have corrected the Doppler estimate here. And thus, the received baseband signal of the satellite, of one satellite, then can be given here now without the Doppler, because we assume the Doppler has been corrected. And we only have now phase, delay, the power of the signal, the symbol of the received signal plus noise in our vector notation that we already have introduced twice. And then if we only use, we will again focus only on the first period of the signal. So we will drop the dependency on k just for developing the maximum likelihood estimator. So again, for this signal, we can build a maximum likelihood estimator that is trying to estimate time delay and phase at this time jointly. We can build again and assume the PDF, assuming that x is a random variable. This is the Gaussian, the multivariate Gaussian probability density function. Again, we can say that the likelihood is equivalent to the probability density function. Remember that this is just changing the perspective. For the likelihood, we have a realization of the random variable x is our signal x, and we're trying to find the parameters that best match this realization. Again, we can instead of maximizing the likelihood with respect to the two parameters, we can also maximize the log likelihood of the parameters, because the logarithm is a monotonic function. Again, we can write this, the first two terms of our cost function here, they're not dependent on phase or delay, so we can drop them. We can then further expand the third term. I did not drop them here, but okay, in principle we can drop them, and we can further expand the third term. We can further expand the third term. And as the first three terms do not depend on tau and phi, and the last term is constant with c of tau norm, the L2 norm of this is constant for any time delay, we can also drop the last term. So we only have the dependency on the two first, on this second term here that we can develop from, or that we can derive from the L2 norm of the received signal minus the model. And we can take and this is the real term of X Hermitian G of 0 e to the J pi, J phi to the power of J phi times C of t. So we have a dependency here on phi and tau, and we see again, this is some sort of cross correlation and then the real term, the real part of it. And we have to find the values for tau and phi that is maximizing this cost function. First of all, we can take the derivative again with respect to phi. This means that in the global optimum of the log likelihood function, if we take the gradient for each parameter, this gradient should be 0 because we have hit the global optimum. So we can take this derivative and write it like this. So if we take the derivative here of this, we can expand the e function into cosinus phi plus j sinus phi times the g0 of x Hermitian c. And this is equivalent to minus the sinus phi times the real part of g0x Hermitian c of tau minus cosinus phi, the imaginary part of g0x Hermitian c. If we equate this to 0, then we can derive here an equation that says sinus of phi divided by cosinus phi is equivalent to tangent of phi, and this is equivalent to the imaginary part of g of 8 of 0x Hermitian c of tau, and divided by the real part of this. And then we can drop as g is real or is either 1 or minus 1, we can drop this g of 0, and we see that this now we have an estimate. We can derive an estimate of the phase with this, right? So it's the imaginary part of the cross correlation of x Hermitian c divided by the real part of x Hermitian c. And finally, we just take the arctangent of this and we can derive an estimate of the phase. We can now plug in this estimate of the phase with respect to dependent on the parameter tau into our cost function again. This makes it look a little bit terrible, but we can now try to further expand this. We can further develop the concentrated criterion, and we can use these. In the bottom, we have two theorems that we can use to expand this. So we first have the log likelihood function here. The composite function is then the real of this. So we just have taken the cost function from above. And we can further rewrite this using these theorems in the bottom. Further expand this using the cosine arctangens of psi times arctangens of psi, while here psi is just is the argument of the arctangent. And we can use now these two theorems that are in the bottom of the slide, reformulate this, and we can arrive. Now this is already looking much better, right? So we have real part of g0 of x Hermitian times c minus psi times the imaginary part of g0 at 0 x Hermitian of c divided by the square root of 1 plus the psi square. Now we can plug in psi again and evaluate this. Now we can further write this as the real part of g of 0 x Hermitian c times the square root of 1 plus psi. This is psi square, so the imaginary part divided by the real part of the cross correlation. And finally, we can rewrite this in this form, and then we get to something that's very simple here, right? So we get to the absolute value of the cross correlation function. That is very interesting, right? So because we can drop the g of 0 here because this is 1 or minus 1. So in the end, it's very simple. The time delay estimate is the absolute value of the cross correlation. So X Hermitian C is the cross correlation between the signal and the replica for a given value tau, and we take the absolute value of that. And thus the estimator for the time delay can also be written. We can not only take the absolute value, but we can also take the absolute valued square. Because yeah, it doesn't matter. So we have this maximization scheme. So we maximize the cross correlation function with respect to tau. If we have tau, we can plug this back into our estimate of phi here, and we receive the estimate of phi. So this is how it works. Yeah. So let's move on to slide 10. So the feedback structure in practice to maximize the cross correlation function of X Hermitian C and then the square root, the square absolute value is a non-coherent delay log loop is used, which is the result of applying a gradient ascent method. And we discussed this already yesterday. So hence a gradient ascent method for the kth iteration can be given. So we take the derivative of this concentrated likelihood function now with respect to tau. And Eduardo, is the screen again locked? I'm on slide 10. Some people in the comments.
I think we are seeing slide 7.
Oh, okay.
Maximum likelihood estimation.
Ay. So I'm trying to. Why is this bad? Okay. Just a moment. I will check something here. Okay. Yeah, then I'll go back to slide 7. Slide 7. Oh, this is bad. Okay. So here's slide 7.
Are you sharing your screen?
Yes.
Now we see only a black screen. I think you need to disconnect, Felix.
Okay.
Sometimes it happens.
Okay.
Just disconnect, please. Connect again,
Okay.
and probably will be okay.
Okay. I'll connect again. See you
Okay,
in
thank
a
you.
short. Okay. I'm back. I hope you can hear me and see me. So I'm trying to share my screen again.
Yes, now we can see you. Probably when you share your screen, everything will be okay.
So I will continue from slide 7 again, okay?
Okay, thank you, Felix.
Can you see the slide 7?
Yeah, we are seeing
Okay.
now the slide 7.
Okay, so I'll continue from here. I'm moving on to slide 8. So the change worked?
Yes, perfectly.
Okay. So what we did is, so I will do this. I will talk through this again. So we have here on slide 7 on the bottom, we derive the phase estimate, and we are now moving on, plugging in this phase estimate into our cost function again, into the original estimator, and this first looks a little bit ugly here, but we can further derive this and we will arrive at a very nice end. So we can now further develop what we can now call the concentrated criterion, LC, so the likelihood concentrated. We have plugged in our phase estimate. We can now call the argument of the arctangent psi here. We can further develop this as cosine of arctangent psi plus j times sinus of arctangent psi. This looks very ugly, but we can use here the theorems in the bottom of the slide to further refine this. So we plug in these two theorems, so we arrive at this formulation, and then we can further refine this to real of g of 0 x Hermitian c minus psi imaginary part of g0 x Hermitian c divided by the square root of 1 plus psi square. Now we can plug in again the argument from the arctangent, and we arrive at this formulation. Now we can reformulate the nominator and denominator, and we get to the real part of g0 x Hermitian c times the square root of 1 plus the square of imaginary of g0 x Hermitian c divided by the real part of this. We can further refine this to this formulation, and now we can see this is just the absolute value of g0 x Hermitian c, right? So it's in the end, and we can then even drop the g of 0 because it's either 1 or minus 1. So very simple in the end, to derive the time delay estimation, the time delay estimate, we just have to derive the cross correlation between x Hermitian c with respect to a time delay tau. We can then finally, the estimator for the time delay is given by maximizing this cross correlation, the absolute value or the absolute valued square. It doesn't matter with respect to tau. If we have this estimate of tau, we can go back to here our estimator for the phase at the bottom of slide 7 and plug in our estimate of tau, and with this we can directly calculate an estimate of phi, the phase. So now we have also derived the maximum likelihood estimator for joint time delay and phase estimation. And in practice, to maximize this cost function, so the x Hermitian c and then the absolute valued square, a non-coherent delay log loop is used, sometimes also a coherent delay log loop. We will focus here in this short part on a non-coherent delay log loop, which is the result of applying a gradient ascent method. Hence, a gradient ascent method for the kth iteration can be given as. And this follows the ideas that we introduced in the beginning of the course. We just have now here the derivative of the concentrated criterion instead of the likelihood. If you remember, we had for the time delay only estimate, we had here the likelihood for the time delay estimation. And mu of tau, again, is a step size, and this is a design parameter. You have to design this. You can choose this step size. I mean, the larger step size, you would converge more rapidly in a to the true value, but you might not be able to refine the estimate after a certain point. If you use a lower step size, the refinement of the estimate is very good, but it will take you more steps. So there's this trade-off that you have to take. The derivative within each iteration is approximated using the central difference coefficient. This is the same as we already introduced in the first part of this course, and again the difference coefficient with respect to 2 delta. So we can formulate the concentrated, we can now plug in the concentrated criterion here, which is just the absolute value square of the cross correlation between x Hermitian c tau hat at k minus 1 plus delta, and then minus the absolute valued square of x Hermitian c tau hat k minus 1 minus delta. So we have again this early minus late correlation that we introduce here. To derive the central difference quotient, the DLL has a correlator pair. These two correlators are called early and late, respectively. To obtain the gradient method using a feedback structure, we consider that the observations are successively collected in intervals with x of k. We also take into account that the parameter tau k is not deterministic anymore, constant over k, but changes for different time instances k according to the satellite motion or user motion or propagation effects. Thus, we can write now this feedback structure. So the actual estimate at time instant k, or the new estimate, is dependent on the time, the estimate at time instant k minus 1 plus mu tau divided by 2 delta, and then this early minus late correlation using the data from the previous time instant and the time delay estimate from the previous time instant. To derive a feedback structure for the phase estimate, we can build a very primitive phase delay lock loop, a PLL. We can a phased lock loop. We can use the maximum likelihood estimator of the phase. Remember, this was the arctangent. Now we include here the phase from the phase correction from the last instant, from the previous time instant. And then this gives us, what does it give us? It gives us the phase difference between the estimate and the true phase. And with this, so the second term tries to estimate the phase estimation error, and is trying to update the phase estimate to correct this error. And we also have to define again here a step size, so mu phi for this gradient method. And this is already the phase locked loop. So we can have a delay locked loop running, and then based on the delay locked loop, we introduce here the result of the delay locked loop at the time instant tau hat, k minus 1. So the time delay estimate tau hat at time instant k minus 1, and we also use the phase estimate at k minus 1, so phi hat at k minus 1. So these are the two feedback structures for time delay and phase estimate. Let's talk about the so this concludes the discussion on joint phase and time delay estimation. Now let's have a closer look at the non-coherent delay lock loop. This is a flow diagram. In our notation, we always had X Hermitian times C, and that's why if we go back now from a vector notation to a notation using sums and scalars, and series of sampled values of the signal, we have as an input here x, k, n, capital N plus n, and then we have to take the conjugate complex because we did that with the Hermitian in our notation. This is not necessary, but we keep this here for our consistency with the vector model. Then we multiply, this is what correlation is doing. We first multiply with the spreading sequence here with the early and the late spreading sequence. So C of k capital N plus n parameterized either by tau hat k plus delta or tau hat k minus delta. And then we perform correlation, which is the sum of this after multiplying, and we take the square of the absolute valued square, and this is exactly the cross correlation that we have calculated before as the estimator for tau. We now perform this, or the feedback structure. We have to take the early minus late. So that's why we sum up, and the late path or late arm here is multiplied with minus. This gives us this what's called the discriminator output, the error signal E of tau, and this is P times, we come back here to the receiver, the loop S curve. This is S here for non-coherent at epsilon tau, which is the time delay estimation error plus some noise. So E of tau and N of tau, these are the error signal and discriminator noise. The S of N is the S curve for the non-coherent DLL. Remember, this is just if our signal model is correct, and this is what we assume here, then this is the autocorrelation function of the sequence early minus the autocorrelation function sequence of the sequence at late. And this is the S curve, and we also have to multiply with the power here. Then this error signal is introduced or is filtered by a loop filter, f of tau of z, and the output signal of this loop filter, u of tau of k, is fed to an integrator that is integrating all these corrections. Because what is the error signal E of tau tries to is an estimate for the time delay estimation error. We will see this later, because we will linearize this. If you linearize this curve around the true time delay, when the time delay estimation error is 0, we can see that this is there's a linear dependency between the error and this observation. So the error signal is quasi is quasi an estimate of the time delay estimation error, and we're trying to minimize this time delay estimation error by driving the loop with this arrow. First of all, we are filtering this with a loop filter to reduce the noise. And then in G of tau of z in this integrator, we are integrating up all these errors because we have to generate an estimate of tau and not an estimate of the error. So we have to drive what's here, the code generator, with the estimate of tau. And this is the integration of all these errors. Yeah. The S-curve for the non-coherent, as I already said, the non-coherent DLL can be given as the absolute valued square of the autocorrelation function of the sequence at epsilon tau minus delta minus the autocorrelation function of the sequence at epsilon tau k plus delta. So then this autocorrelation function in our discrete signal model can be given like this for the early, and this is for the late correlation. So we correlate either the true time delay tau of k, either with tau hat of k plus delta or with tau hat of k minus delta. And delta is the tracking error. So, epsilon of tau is the tracking error, and this is tau minus tau hat. Yeah, the noise component is a little bit more tricky to calculate. So n of tau is, we can calculate here an early noise component and then late noise component. And this is then early minus late, and we can derive this with these terms here. So we have the early and the late component. These are the correlations of the signal, of the replica with the noise. So we have here the early noise component is 2 times the square root of p g of k r, the autocorrelation function of the sequence at epsilon tau k minus delta times cosine phi of k. Now we, in this writing, we also assume now that phi is changing with the periods times the real part of n tilde e and the n tilde early of k, and this is defined in the bottom. So this is the cross correlation between the sequence and the noise, plus the sinus of phi k times the imaginary part of n tilde early of k plus the absolute valued square. This comes from the squaring operation. Yeah, so this a rather complicated noise model is introduced by the squaring operator here at the end of the two correlations, because the noise comes in with x here. Then we multiply the noise with the sequence, and then we have the summation and the squaring. And then to calculate n of tau is getting a little bit more complex because of the square, absolute valued square. But okay, we can write it. So this is then the definition of the discriminator noise. Yeah, let's have a closer look into the loop filter. I will not go into much details, but in principle, this is a weighted integrator, and this can have higher order, so the mth order. In our case, filter is a so-called higher order weighted integrator and can be given by this formulation in Z domain. We have here the coefficients of the filter A tau m. That we can use for the design of the filter, and the Z transform of, it's the Z transform of this is the Z transform of the filter response. An estimate of the time delay at time instant k can be given by, so we have this more general formulation. This is the output of the, that's the output of the filter, of the loop filter. And then we have a gain from the integrator, and then this is just integrating. So this is the integrator here. So the time delay estimation. So we have the previous time delay estimate at the time delay estimate at k minus 1 plus this integrator gain times the input to the integrator. And then using the Z transform for this, we can write this. So with capital letters, so we have T of Z is equal to T hat of Z times Z minus 1 plus KG of tau U tau Z of Z times minus 1 to the power of minus 1. And by this, we can derive the transfer function of this integrator here. So the integrator G of tau is given by Kg tau, which is the design parameter now for the integrator, times Z minus to the power of minus 1 divided by 1 minus Z to the minus 1. In order now to design the loop, we have to figure out what are the values for K, G tau, and A tau M, the filter coefficients for the loop filter. Yeah, let's have a look at the phase locked loop. So how is the phase locked loop connected to the delay locked loop? We need the time delay estimate from the DLL to perform correlation with the signal and then feed this signal into the PLL. We are doing this here in a way that we have the incoming signal enters the PLL, and we have also a generated replica coming from the DLL already with the time delay estimate at time instant k. We can then see that in this block diagram, the DLL produces the time delay estimates and the PLL produces the phase estimates. As the DLL is non-coherent, the phase estimate is not fed back to the DLL here, and this is according to the maximum likelihood estimator. This is not necessary. The DLL provides a reference signal C of k capital N plus N parameterized by tau hat at time instant k to the PLL. Besides the early and late correlation included in the DLL, the PLL includes the so-called prompt correlator. In our model here, the DLL includes another correlator with the replica provided by the DLL, and based on this correlator, we're doing our phase measurements. So here is the PLL construction, or the overview, the flow diagram. So we have the incoming signal, we have the replica coming from the DLL. With the current time delay estimate, we perform correlation, so the sum over n0 to n capital minus 1. After that, we multiply with the current phase estimate, pass this into the what's called discriminator. In our case, this is this arctangent of the imaginary part of it divided by the real part of it, and we have a minus here. Be careful if you go into the literature. The arctangent does not have the minus inside. The correction of the phase has to be a minus, and the conjugate in the beginning, in the entrance, will not be there. So this is the standard formulation, but I included this conjugate because we had this in our if you remember, we defined our discrete model with X Hermitian, so I kept it consistent here. So we have here the conjugate in the beginning, and then we have in the loop, we have a slightly different formulations than from the standard literature. We have here also the error signal at the output of the Arcus tangent. This is then the phase error. This error signal is contained by the phase error epsilon phi, which is phi at k minus phi hat at k, and we have also noise, the discriminator noise. We also have here a loop filter that is usually used to reduce the noise of the discriminator output, so to make n phi smaller. And the output of this filter is entering the integrator. The integrator is integrating all these phase errors estimates or filtered phase error estimates, and by the integration of this, he can generate a new phase estimate phi hat of k that is then used in the loop, and we can close this feedback structure. The so-called, and this is from the headline of this, or from the title of this slide, you can see it's called Costas PLL, and this is because we're using the arctangent as the phase as the discriminator here, and is insensitive to the navigation message bit. So you can estimate the phase without influence of the data bits, and that's very important if you want to work with data channels, but also with pilot channels. Yeah, we can also have, the definition is very similar here of the loop filter. It's a higher order integrator. We have now filter coefficients A, phi of m. This is for our design of the loop. Then again, we can also define here the integrator as for the DLL with phi of k, the phi hat of k equals phi hat k minus 1 plus a gain from the integrator times the introduced signal from the output of the loop filter. And then if we transform this to the Z domain, we can write this in the Z transform, and at the bottom of the slide we can again derive the transfer function of this integrator. And in order to design the loop, so we have chosen, usually for the design of the loop, you have to choose a discriminator. We choose the arctangent. There's different variants how to perform phase error estimates. You can do this also in different ways than we did. We followed here the maximum likelihood concept. But in a real implementation, maybe the arcus tangent is difficult to achieve numerically, so you can choose also other implementation that approximate this. So the choice of the discriminator is up to the user or to the designer, and then we can here also use the filter coefficients of the loop filter A phi m, and the gain of the integrator k, g, phi as design parameters for our loop. Yeah, now we have assumed so far, we have been talking about joint delay and phase estimate under the assumption that the Doppler estimate was sufficient enough provided by the acquisition, and that the Doppler was not changing over time. But now let's introduce the Doppler to this theater, to this exercise. So now the Doppler frequency is changing over time, and we could introduce something called like a frequency lock loop. Additionally, the acquisition provides an initial estimate of the Doppler shift. This initial estimate in general is not exact enough, or as the satellite or the receiver is moving, the Doppler shift is changing in time or over time. The estimate of the Doppler frequency shift needs to be refined and adapted over time. So we need to have a Doppler tracking, frequency tracking. The Doppler estimate can be refined using a feedback structure, and the Doppler frequency shift is corrected before feeding the signal to the DLL and PLL. And initially, the estimate of the Doppler provided by acquisition is used and then updated over time. As I already said, I will show here a structure with DLL, PLL, and FLL, but this is just one choice. Most of the receivers that you will encounter today, they just have a DLL and PLL, and they track also the phase, the frequency change with the PLL. We can see that when we look at the derivation of the FLL now. There's also receivers that switch between FLL and PLL, so they first try to refine the Doppler estimate and then start the phase estimate. As you have seen, the phase estimate is not necessary for the delay locked loop, but the frequency estimate is necessary to be fed back for the delay locked loop to work, because we need to maximize correlation. If the frequency offset, so the Doppler offset, gets too large, the DLL will lose lock. Also, the non-coherent DLL will lose lock. So we need to feed back at least the Doppler correction, but we do not need to feed back the phase correction. This is because of the squaring in the DLL branches, the early and the late branch. So we see here now the architecture with a PLL and an FLL. So we have the feedback of the estimated Doppler frequency back to the before the DLL and the PLL. And this is what you, in the literature, sometimes is meant with Doppler wipe-off. So they are correcting the Doppler. This is what I meant in the beginning of this lecture with correction of the Doppler. So we are multiplying the incoming signal with e to the j2 pi k capital N plus N, and then Ts for the various. And then we have to introduce here the Doppler where the dot is. This is in the literature, a lot of times the Doppler wipe-off is with a negative sign, so with an e to the minus j, but this is because they don't have this conjugate operator in the beginning on the incoming signal. I kept this here again for consistency with our vector signal model. Yeah, then this Doppler corrected signal is fed to the DLL and to the PLL. The DLL is also providing, again, the prompt correlator signal to the PLL, and is also providing, we are using the output of the prompt correlator also for the FLL. So this is the next arrow down to from the PLL, the connection from the PLL to the FLL is the output of this prompt correlator. Then the three loops, they output time delay, phase, and Doppler, while only the Doppler frequency is fed back in front of the DLL and PLL. But okay, as I mentioned, this is only one choice of the architecture. You could also just cut out the FLL here and just feed back the phase estimate at any time instant. And this also would correct phase and Doppler then in front of the DLL and the PLL. Yeah, after initialization, the Doppler correction based on the estimate provided by the acquisition, we can further refine the estimate based on the time derivative of the phase. Yeah, because the derivative of the signal phase is the frequency, is the Doppler frequency, is the change over time of phase. Yeah, so as an estimate of the Doppler frequency, we can now take two phase estimates at consecutive time instances, divide this by 2 pi, and then the duration of the correlation, or in our case, this is in the literature called the coherent integration time. In our case, this is equivalent to TD, which was the length of one sequence. But this could be also several sequences in practice. But we are working here with the duration of one sequence, and this will provide us an estimate of the remaining Doppler frequency after of the Doppler frequency. Introducing the MLE of the phase, we can write now this in a different way, And alternatively, we can also write and say, okay, we can take the tangent of this difference and then apply the theorem in the bottom, and we arrive at the tangent of phi hat k minus tangent of phi k at k minus 1 divided by 1 plus the tangent of phi hat k times tangent of phi hat k minus 1. We can now take this formula and introduce as you remember, the phi is the Arcus tangent. So the tangent times the Arcus tangent is again the argument. So we can come up with this formulation here. We can refine this to this by multiplying with here the denominator and so on. We can get to this formulation. And finally, we can then write this as the Arcus tangent. So we just take the Arcus tangent of this to come back to, because this is the tangent of the phase difference. If we take the Arcus tangent of it again, we arrive at the phase difference again. And these two values Q and I are given by these output values of the prompt correlator. And that's why we had to feed the output of the prompt correlator from the phase lock loop, from the phase lock loop to the frequency lock loop. This is the discriminator of the phase lock loop, frequency lock loop, the FLL. This argument of this Arcus tangent function, and the interesting thing is that it is also independent of the bit transitions of the signal. And then we can build now here our FLL structure. So we have this time we have the feedback of the Doppler frequency we have before the DLL, and inside the DLL, inside the FLL, the prompt correlation is performed, and then afterwards in the FLL, the Arcus tangent discriminator is applied. We have them again an error signal at the output of the discriminator, where epsilon nu is the Doppler frequency error. And we also have with n nu of k discriminator noise. We have some loop filter and integrator again, also the same as for the PLL and the DLL. And the FLL is insensitive to navigation message bits, which is very important for our application. Yeah, again, we can build the design of this loop filter again as an mth order loop filter with filter coefficients now a nu m. And again, we can build using the state equation and then the Z transform, the transfer function of the integrator. And again, we're integrating here, starting initializing. This is the only thing that is we're initializing. It's the same as for the DLL. We are initializing this loop with the estimate from the acquisition. Yeah, and then the correction, the Doppler correction is updated after the integrator and the loop thus is closed. Yeah, loop transfer functions. These are important, and this is the last thing that I will introduce today. These are important then for our design. We will have a quick derivation of the non-coherent DLL loop transfer function, because we have here the complete formulation. If you go back to the slide of the DLL, we can see that the output of the loop before the new estimate of the time delay is fed to the code generator is tau hat at time instant k, and this is a result of the error signal now here without noise, the error signal, which is p times the loop S curve dependent on the error, the time delay estimation error. And then this is convolved. So this star here is convolution convolved with the filter, the loop filter, and convolved with the integrator, right? So the output of the integrator is the convolution of the output of the integrator, which is the tau hat of k, and this is the complete let's say how the error signal after the discriminator is processed by the loop filter and this integrator. Now we can linearize this, because now here in this formulation we have no direct connection between the DLL error and the discriminator output, and so to the time delay estimate. So now we can linearize this, and we can say, okay, the this loop S curve is linear around the true value. Okay, and we say, okay, we linearize around this, and the true value is achieved if the error is 0, right? So the loop, we can take the derivative. This is given here by the Sn prime. So the derivative of the S curve of this non-coherent loop for an error 0, and then multiplied with epsilon tau, which is the loop, the delay estimation error. So this is a linearized version. We are linearizing the S curve around this zero estimation error. And I think this is reasonable, because if we have initialized the DLL well, then we should operate in this linear region of the S curve, and then this linearization is valid. And is a very good approximation of this behavior of the loop. We can then now take, as we have no noise involved, we can take the Z transform. We have to be careful with the Z transform, because theoretically the Z transform of Gaussian noise does not exist. So using the Z transform now, we get, as there's no noise involved, we can write the complete transfer function of the loop, or the behavior of the loop in the Z domain. And based on this, we can derive here what's called the closed loop transfer function h of tau of Z, which is the input, which is the true time delay, divided by the output, the estimated time delay in Z domain. And then we have here the behavior of the closed loop. This is important to be derived for the design of the filter parameters, so the loop filter parameters and the integrator parameter, in order to design the behavior of the DLL. So how fast does the DLL manage to get to the equilibrium? How fast does it manage to track the true value and keep the track also under dynamic conditions of the delay? I will not go into further details of the design of these loop filters, but I will stop here for today. We can further visualize again the loop S curve for a non-coherent DLL, and this is given for a GPS CA code signal or Galileo E5B signal. This is looking pretty much the same, with early late spacing of the DLL of 0.5 chips, and then we arrive at this loop S curve with vis-a-vis or versus the tracking the delay error. This should be epsilon tau here, I'm sorry. So it's epsilon tau and in the S curve, and epsilon tau also on the x-axis. And we see here that around where the error is 0, around this point, this S curve is very linear. So this approximation of the S curve as a linear function is justified for small errors. For errors up to maybe, let's say, half a chip here, or a little bit less than half a chip, this is justified. And then delay estimation error of half a chip is already very large. So the loop should be designed already to work in this linear region. Also, the SNR of the signal should be sufficient enough. So the design of antenna, amplifiers, and front end should provide an SNR that is sufficient to initialize this loop in this area and to also keep track of this area. This linear region is sometimes also called pull-in region. So we have to initialize the DLL in this linear region also. So we have to pull in the signal in this linear region. Otherwise, our loop would diverge, or the linearization is not valid anymore. Yeah, for the phase-locked loop, we have not this problem that we have to linearize something, because at the discriminator output, we just have the phase error plus noise. Now, if we drop the noise, we can just have here the output of the discriminator on the right-hand side, and then this is convolved with the transfer function of the loop filter and the integrator to derive a new estimate. And using the Z transform, we can also derive the closed loop transfer function with this manner. So the closed loop transfer function here is then only dependent on the integrator and loop filter transfer function. The same thing for the FLL, very similar. We just have here the Z transform of the Doppler signal, then is nu hat n hat of Z, and we can also derive the transfer function of the FLL here. So this is where I stop in this training. The design of the loop filters and so on, you can maybe continue reading in the literature. This is a not so easy field. A lot of people, they take already coefficients of these loops from the literature. There have been people deriving optimized loop filter structures already, and you can just take the coefficients from tables and introduce them to your loops, dependent on there's values, for example, the loop bandwidth, the damping factor, and all these things. And this defines the behavior of the loops, how they reach equilibrium. So how do they reach the true parameter estimate and keep track of this true parameter of this true parameter. So be close to the true Doppler value, have an estimate that is close to the true Doppler value, have an estimate that is close to the true phase value, have an estimate that is close to the true delay value. Yeah, so we have worked ourselves through the basic signal processing also, where I will just show this overview here again, where from this structure at the output here, we have delay estimate, phase estimate, and Doppler estimate, and this is what will be used by the positioning for each satellite to calculate position. On top of that, we can also estimate the power of the signal. This is also used in the positioning. So this would be a fourth estimate for each of these satellites that we receive. So we have to run this this tracking in parallel. So for each satellite, we have to perform this tracking. We also have to perform estimation of the power of the signal, but this is easy. Can also be done with the prompt correlator output, as we had seen there with the. We can estimate also the amplitude of the signal, and based on all these estimates, positioning can be achieved. And this is where I hand over now to my colleagues from the University of Politècnica de Catalunya, for UPC, Adrián and Jaume. They will guide you through the next 2 days, looking into positioning and precise point positioning, and where you can also apply with the software, you can have a hands-on experience. So take advantage further of this course. So thank you very much. I could not see because I connected again. After I connected again, the chat was deleted for me. Eduardo, maybe you can still see the complete chat and let me know if there are some questions, so I can also take now some questions. I think we still have some time left. Oh yeah.
Okay, Felix. Actually, we don't have questions in the chat. I don't know if everybody is understanding everything, or maybe they are shy. But I think we have time for the final remarks, and then we can finish this third day of the training.
Maybe I start. Yeah, it was a pleasure to give this course. It's only a quick introduction in the signals and signal processing part. I mean, there is more things to be considered, especially as you have seen in the end now, the design, the detailed design of the loops and so on. There's also, you can extend this to Kalman filters also for the tracking. But I hope that the slides will help you to understand what is done in a GNSS receiver. It will hopefully also help you to develop your own ideas about this. This is what it is about. I thank you for your participation, for your questions. If you have further questions, you can email me or write to Mundo Geo or to the GIC platform or the GIC, the Galileo Information Center webpage. We'll continue answering your questions. I also thank Eduardo. Many thanks for organizing the webinar. It is a pleasure again to do this, and I hope this will be also useful for the audience in the future that maybe will also watch the YouTube video. So I hope this will be a good introduction to people.
Felix?
Machine learning. Yeah, machine learning is something.
Yes, we have a question.
That is, so the question is there an application of machine learning in this work? Definitely, machine learning can be used to enhance tracking, can be used to extract and identify patterns of the parameter estimates, for example. So categorizing this, machine learning can also be used to enhance the tracking in a sort of way, because the DLL in the end is a sort of Bayesian estimator, and then we can move on to also machine learning, especially then in difficult environments and so on.
Okay, thank you. And there is also a comment from Fabio Fagundes that math is the universal language. So it's a lot of math in this lecture, but it's universal.
Yeah, I try to. So don't be afraid of the math. I try to explain what it's for. But yeah, it's a language that is precise, and I usually like it to have a I mean, we can also explain this in words, but I think the way, and I choose a specific way of showing. There's many ways of deriving the feedback structure. I took this way I took this path to introduce a maximum likelihood estimator and then develop this into a feedback structure. We could have started with a Bayesian estimator from the beginning and then derive the feedback structure directly from this. And we can also link all the DLL, FLL, PLLs to Kalman filters, because these are Kalman filters with a fixed Kalman gain. So you can also have a link to Kalman filters very fastly, but yeah, we're out of time if we do this, but this is all connected. So keep in mind, this is just one interpretation of it or one way of getting into it. I thought it's an intuitive way from my personal experience, and I just try to give this experience to you. How I approach this, but in the end, you will see that this is linked to Bayesian estimation and then also to Kalman filtering.
Okay, thank you, Felix, for your answers. Adria and Andre, maybe you can talk just a little bit more about the opportunities for master and PhD, because there are people that connected after the break, after the Q&A, the first Q&A session. So if you could just give a little introduction about these opportunities, this would be good for people that were not in the first part.
Mm-hmm. Okay, so let's try to summarize a little bit, and then in the same way as we did in last time. Yeah, so we will have soon openings for new master and PhD topics in UFC in collaboration with ITA, where Professor Felix is, and with UPC, where Professor Adria and Professor Jaume are. And this is a joint cooperation project that fits in the context of GIC. We will, if you are interested in doing a master or a PhD in topics related to GNSS, write to us. So to me, the emails, I think I will type again here, but I think we have provided that before. So this is my email. I have just put it in the chat. If you have any question about that, don't hesitate to contact us. There is a selection process upcoming that would take place maybe in early August. So we still have some time for that, and the selection process runs every semester at UFC side at least. And then once the student is enrolled in the master or in the PhD, the student can apply for a scholarship that can be funded by the Brazilian funding agencies, public agencies like CAPES, CNPq, or the state funding agencies of Ceará, FUNCAP. And the students can have also the opportunity of doing internship in ITA or in UPC in the context of a double PhD agreement in the case of a PhD research. Regarding the subjects of the research, we are defining subject at this time. Felix and I will soon launch the subjects for Masters and PhD for the next selection process. So please, if you want to know more about it and if you are interested, just write to us, and we can eventually get together with the different candidates and then provide more detailed explanations. So maybe this can be done in a separate meeting after this professional training. At the convenience of everyone, we can provide you more information about that. I will maybe Adria can comment a little bit about that, this joint supervision. But I think that's more or less to summarize more or less what we have said during the break.
Yes, exactly this. To have a supervision, a co-PhD means that you have two supervisors. You have a supervisor at the Brazilian university and a supervisor at the Spanish university. And this means that you have to fulfill the requirements of both universities. And for this, there are agreements already in place between the universities, but everything starts after finding a candidate. So we cannot give more details until we do not see your background, if you fulfill the requirements or not. And for this, it's very important that you proactively contact us, and then we can start the process. This is to complement what Andre already said. And regarding the training, I really want to thank Felix for these 2 very intensive days of lectures. And now we are in the equator, and we will transition to the navigation part, to what do we do with these measurements and these estimates that Felix was introducing, how to proceed with them. Also, just to remind that these lectures are recorded, and there will be on the GIC website, together with the PDFs, the software, everything will be in the website. So you can go again through the entire lectures, and we are always welcome to answer emails and so on. So don't be shy now if there are some questions that appear later next week or in another moment, don't worry, that we will not disappear. So that's everything from my side. We continue tomorrow.
Okay, we thank everyone for participating in this 3rd day of the professional training organized by Galileo Information Center, Brazil, together with UFC and UPC. Thanks also to the speaker, Dr. Felix, for your presence and your time, and also to André and Adria for the information about opportunities for masters and PhD. We remind you that the materials are already available for you to download from the event's website, and also the replays of the other days. And we await everyone's presence tomorrow for our 4th day of the training at the same time. See you tomorrow. Bye.